Hi, welcome to the next lecture in the NPTEL series on Haskell. In this lecture, we will be looking at uh, a few problems in graphs. As I mentioned in a previous lecture, we are now moving away from learning only Haskell to learning some general problems and some most often used data structures and algorithms and rendering them in Haskell. Okay, and we have already seen several problems being solved by means of lists. You are given a problem, you represent it as some data types or data structures based on lists, and you solve them. Many problems require you to represent the problem as graphs and do run some algorithms and graphs. We are just going to spend one lecture on it and look at a few important uh, uh, problems. We are especially going to look at problems where Haskell makes it much easier. In particular, the laziness of Haskell allows you to write a very simple algorithm, but Haskell will ensure that it is run efficiently. Okay, let us get into the material. So recall that Haskell uses lazy evaluation, which means that you do outermost reduction. So if I have 2 plus 5 times, no, this is a bad example. If I have factorial of 3 plus 2, rather than actually reducing 3 plus 2 to 5, what Haskell would do would be to say this is equal to 3 plus. Actually, this is a bad example too, because factorial depends on whether the argument is 0 or not. That determines which rule will be fired. So it has to actually reduce 3 plus 2 down to a number. But I'm sure there are examples where you can, a better example is this. If you define double of x to be x plus x, double of 5 is double of 5 plus double of 5, and then it is 5 plus 5 plus. Yeah, this is how it will do. It will not do the following: double of 5 plus 5. Okay, so this is what outermost reduction means. Looks like this is wasteful, but no, Haskell has a way to do it efficiently. The important point is that it will not do any work that is not necessary. So the thing is, simplify function definition first, compute the argument value only if needed. Okay, so now this is lazy evaluation. We will see how lazy evaluation helps when we try to represent the notion of a graph and when we try to solve some problems involving graphs. So graph G is defined by a set of vertices V and a set of directed edges E subset of V cross V. So I might have, and typically you would draw it as pictures. That's a graph. So you might give it names like this, and you have edges from 1 to 2, 1 to 3, 4 to 1, 2 to 4, 3 to 4, and 3 to 2. Okay, so you would express this graph as two sets. The vertex set is 1, 2, 3, 4. The edge set is okay. So graph is given by two sets like this. So assume that, so for simplicity, since we are just going to look at some simple problems, assume that each vertex is represented by a character. So it's limited, but it's fine just to illustrate some examples. So in Haskell, you would actually render it by saying type vertex equal to char. Recall that type defines type synonyms. not a new type. So, vertex is another name for char, at least as far as this program is concerned. Edge is another name for the type of pairs of vertices, and vertices are given by so here we said set, but in Haskell sets will be translated to lists. Okay, so vertices are a list of vertex and edges is list of edge. Okay, so that's the type, and I have to define my vertices and edges, so I would give them as lists. For instance, I might say vertices is A, B, C, D, E, F, and edges is all this. So let's try to draw this graph. So A, B, C, D, E, F, let's say. And I have an edge between A to B, A to D, B to C, F to D, C to A, C to E, D to E, and F to E. Right? That's my graph. Maybe you can draw it better, but this is my graph. And let's draw this better. C to E should actually look like this. Okay, so that's a graph. And given a pair, given two vertices, I need to know whether there is an edge between the two vertices. And this is simple because edges are given by lists of pairs. So all I need to do is, if somebody gives me u and v, I'll check whether the pair u comma v is an element of edges. Okay, so that's basically it. And now we want to solve a problem, connectedness. Okay, this is a function of type vertex or a vertex or a bool. What it asks is given vertices u and v, is v connected to u? Or in other words, is there a path from? Okay, so this is the question. What is a path? A path is something like you start at a vertex, you take an edge, you go to another vertex, you take an edge, you go to another vertex, you take an edge. That's a path. Okay, so you have u here and you have v there. Is there a way you can keep on traversing these edges and start from u and eventually reach at v? So connected uv is true if and only if there is a path from u to v using the given set of edges. Now, how do you define connected uv? Here is a mathematical definition. You might say that, okay, here is an inductive definition that you might give for connected. This is not a program yet. I am saying if there is an edge from u to v, then v is connected to u. If v is connected to u and there is an edge from v to w, then w is connected to u. Okay, so this is my program. So you might want to say this is hard to write. As stated, this is not a program in Haskell because you are sort of saying you might think of it as like writing some logical statement like this. Right, but that's some logical statement. It's not. This is not a program in Haskell. Okay, so you need to find a way to actually program this in Haskell. Okay, so how do we do this? Okay, to check if u is connected to v, v is connected to u, you might do the following admittedly very inefficient algorithm: build all paths in the graph and check if there is a path with first vertex u and last vertex v. Okay, so that seems like an algorithm, but the set of all paths is infinite potentially. Why? Because if I have a graph where etc., you see that you can take this path, let me change color, you can take this cycle as it's called, and you can go around the cycle any number of times and then exit the cycle. So potentially speaking, there are infinitely many paths because you can go around such cycles any number of times as you want. So how do you solve this? Here is the nice thing, Haskell's laziness, we'll show how to use Haskell's laziness to ensure termination. Okay, what we want to do is build paths by induction on length. Okay, length of a path is number of vertices in the path. So how many paths of length 0 are there? None, right? Because a path should have at least one vertex in it. It might have one vertex alone without any edge, but at least it must have one vertex. So length 0 paths are none. Length n plus 1 paths you can figure out, right? So how do you build a length n plus 1 path? Build a length n path and try to extend it in all possible manners. Okay, so if I have a path already built in my graph, and if from this vertex there are 4 outgoing edges, then there are 4 paths of length n plus 1 based on this path, but there might be multiple paths of length n. So for each of those you will have several extensions of length n plus 1, so there will be multiple paths of length n plus 1, right? So there is only one path of length 0, the empty path. You can extend a path of length k to length k plus 1 by adding an edge. So if you extend a path, you will get a list of paths, because as I told, you could go here and from here there might be multiple outgoing edges. Each of those constitutes an extension. So by the way, when I say length of a path is number of vertices counting repetitions. Right. So if I have, for instance, here, if I have 3 vertices and you can go round and round and round here. So a path of length 0 is just the empty path, path of length 1 is A, path of length 2 is AB, path of length 3 is ABC, path of length 4 is ABCA, and you can actually go ABCAB, ABC, etc. Even though there are only 3 vertices, you can have paths of longer and longer length, because the way we count length is the number of occurrences of a vertex in it, not the number of individual vertices that occur. Okay, number of distinct vertex, number of vertex occurrences counting repetitions. Okay, that's the point. So how do you extend path? This is some simple Lisp programming. So if I have the empty path, then I am not constrained in any particular manner. So if I want length 1 paths, every vertex can be considered as a length 1 path by itself. So extend path of empty list is all singleton lists V, where V comes from vertices. Extend path of V colon V is, suppose I have, so rather than extend at the end, I am going to extend at the beginning. So if I have a path and if there are so many edges incoming to the first vertex of the path, then I will have 3 paths like this. So that is what this says. Extend path of V followed by V is nothing but U followed by V followed by V is such that U is in vertices and there is an edge between U and V. Okay. So now we know how to build paths of, if I am given a path of length k, I know how to extend it to several paths of length k plus 1. Okay. Now if I have several paths of length k, I can extend them to several paths of length k plus 1, and the way to do it is to just say concat map of extend path. Recall that map extend path, if I have 3 paths of length k, let us say L1, L2, L3. Okay, path 1, path 2, path 3, let us say. and let us say path 1 can be extended to path 1, path 1, 2 and path 1, 3. Path 2 can be extended to path 2, 1, path 2, 2. Path 3 can be extended to path 3, 1, path 3, 2, path 3, 3, path 3, 4. Let us say there is 3 ways to extend path 1, 2 ways to extend path 2 and 4 ways to extend path 3. Then what will happen if I do map extend path on this list? What I will get is a extend path. Remember, from P1 it will give you the list consisting of P1, P2, P11, P12, P13. So I will have P11, P12, P13. Extend path applied on P2 will give me the list P21, P22. Extend path applied on P3 will give me the list P31, P32, P33. Right? These are all the paths of length k plus 1. And now I have a list of paths. Instead, I just want a list of paths. So I will concatenate. Concat of this will give me P11, P12, P13, P21, P22. Right? So I would have to say concat of map of extend path. But concat map is a built-in function which is just nothing but concat followed by which is map followed by concat. Okay, this is such a commonly used pattern, map followed by concat, that Haskell offers a single function which is defined to be concat dot map. First apply map and then apply concat on the result. Okay, so now we know how to extend a single path to multiple extensions. If I am given a list of paths, I know how to extend all the paths and get another list. I had a list of all k length paths, now I will get a list of all k plus 1 length paths. Okay. Now, there is a function called iterate in Haskell, which is part of the basic prelude of Haskell. Its definition is this: iterate takes a function and an initial value and it repeatedly applies the function on the initial value. And it works like this: iterate of fx is x followed by iterate of f and f of x, right? So originally you will have, so if I do iterate of f on x, I will have x followed by iterate of f and f of x. So then that will be x followed by f of x followed by iterate of f of x. So that will be x followed by f of x followed by f of x followed by iterate of. Yeah. So iterate of fx will give me x followed by fx followed by f of x, etc. Suppose I have suppose I do iterate of plus 5 of 0, then I will get the list 0, 5, 10 and it will go on, and it will keep on going. Okay. So now why do I bring this function iterate into the picture? Because all paths, I want all paths, right? All paths in the graphs are just nothing but the empty path extended in all manners. So you will get all the length 1 paths. This is the empty path, right? So I start with the list containing the empty path. Okay, that is my first, right? Give me all the length 0 paths, that is the list. If I extend all these paths by 1, I will get some other list. We can call this L. Several paths. These are list of all, L1 is the list of all length 1 paths. I apply extend path again, I will get L2, which is the list of all length 2 paths. Right. So, if I start with the list consisting of the, this is the list consisting of the empty path. And if I repeatedly keep applying extend all, in other words, if I iterate extend all on this, then I will get a big list of paths. I will have L0, L1, L2 dot where L0 is length 0 paths, length 1 paths, and in general Li will be length I paths. Right. So, now I have a way of generating all paths actually. Okay. You could actually try this, and if you try this in GHCA will keep on printing whatever path it encounters. But now remember, we need to figure out whether V is connected to you, but before that we can actually program these things and try to run these things for you. Let me go to Visual Studio Code now, and let me go to this where I have already written these programs. See, I have vertex is a character, just another name for character, edge is another name for pairs of vertices. Vertices is given by A, B, C, D, E, F, and edges are given by this list. And there is an edge between U to V if U comma V is an element of edges, and path is just a list of vertices. Okay, so now I am here is the function to extend path. Extend path of empty list is just all vertices. Extend path of V followed by V is U followed by V followed by V such that U is a vertex and there is an edge between U and V. And extend all is just concat map of extend path. Empty path is the empty list. So, now all paths are given by start with the list consisting of the empty path and extend all, keep on iterating extend all. Okay. Now, let us just check how this works. Okay, it is compiled and I can say all paths. Right. So, I have taken the first 100 paths, okay, and you can see that these paths can loop in all possible manners, ABC, 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 right. This last path is keeping on looping, and at some point of time it decides to exit the loop and say ABC, A, D, E, okay, and maybe that is also a loop, who knows. And so, these are all, so when I say take 100 all paths, notice the following, maybe I should take 20 all paths, so that it is easier to see what is happening. Remember, take will take the first 20 elements of the thing. So, this is the list consisting of the empty path, right. This is the list consisting of all length 1 paths, right. Here you have the list consisting of all length 2 paths. Conveniently, each path is our vertices are characters, so each path is just represented in that string notation. This is all the length 3 paths. Here you have all length whatever 10 paths or whatever. Yeah. So, here you have all the length 10 paths and so on and so forth. Here are all the length 20 paths. Yeah. Okay. So, you have all the length 20 paths here. Okay. Good. So, now how do we solve connectedness? Remember, we wanted to check if there is a path which has the first vertex to be U and the last vertex to be V, I'm not saying this is the most convenient or this is the most, there are much more efficient ways to check if a vertex V is connected with the vertex U. But that is not the aim. The aim here is to show how you can represent graphs and you can actually use the laziness feature to generate some infinite list, but effectively you will use a finite portion of that infinite list to do a check. Okay, so I have this. Now, if there is a path from U to V, there is a path with utmost n edges. Why? Because if I go from U here and I have a path which might go through some loops, which goes through this loop so many times, and then maybe it exits and goes back and does some loop here, and then exits some way and then does another loop, and eventually reaches V. Then what I can do is I can cut out all the loops, and instead of going here and then going there and coming back and doing this, you could directly go here. And instead of going through this loop, you could directly go to V. Okay. If there is a path with loops, there is a path without loops. Right. And the vertices, you can take the first vertex and last vertex can be the same, but none of the intermediate vertices can repeat. So all the intermediate vertices are distinct. And not equal to U, not equal to V, which means that the number of intermediate vertices are n minus 1, n minus 2, n minus 2 intermediate vertices. And then you have 2 vertices here and there, but we missed out one thing, U could be equal to V, right, in which case you are just saying that intermediate vertices are all distinct, none of them is U. So you can certainly say there are at most n minus 1 intermediate vertices and there are 2 vertices at the end, so that makes it n plus 1 vertices. If there are n plus 1 vertices, there will be n edges. Okay, so this is the point. So if there is a path from U to V, there is a path with at most n edges, and right, so or in other words, n plus 1 vertices. So recall that if I do take, then that will produce a list of all length to the list consisting of take n plus 1 all paths will produce list 1, list 0, list 1, list 2. Right, where n is the length of, n is the number of vertices. So you do length vertices plus 1 and you take that. So now I have this list of lists, now I can make list of paths. I can make it into a single list of paths by doing concat. Okay, so this will give me all short paths. Okay, so short paths are all paths with at most n edges. Okay, and I can now compute all connected pairs really. So connected pairs are U colon P such that U colon P belongs to short path and V belongs to U colon P. That's all. This is an extremely inefficient algorithm, that is fine, but I am able to express this algorithm in terms of infinite lists, and Haskell's laziness ensures that I don't need to actually compute infinite lists because concat, because take etc. works even though the list could be infinite. That is really the point. Okay, and even iterate doesn't completely construct the thing, it will only supply whatever is necessary for take to do its action. Okay, so take is lazy, iterate is lazy, all these are laziness ensures that our function terminates. Okay, this is the important lesson. Let's go here. And I have also programmed this connectedness here, because short paths I have defined exactly this, connected pairs are this, and if you want to check whether something is connected, I will just say uv such that the pair u comma v is an element of connected pairs. Okay, so now I can actually go here and check. Yeah, it says true, and I could even say connected pairs. There will be lots of repetitions though. Right, all these are the connected pairs. Okay, and if I want to remove repetitions, I could just say nub. Nub is a built-in function. It is in data.list, and what it does is, nub means essence. So if I have a list, it will remove all duplicates and it will only give distinct elements of that list. Okay, so right, I can now ask for connected pairs. Yeah, these are all the connected pairs. This is a list without repetitions. Okay, good. So this is one problem. Let's look at another problem. This is the next one is a fun problem, and it is also sort of related to graphs, because lots of problems, even though on the surface it is not related to graphs, you can think of some kind of representation in terms of graphs in the background. Okay, so let me move to the other problem next. So this is a search problem, and in general, even the earlier one was a search problem, but here we'll look at a fun example of a search problem. So there is no closed form for the solution. You cannot just write connected equals this very tight this thing. So you need to really go through a cycle of expanding out possible solutions and undoing partial solutions when you reach a dead end. And this is clearly illustrated in the next problem. This is called backtracking. Okay, because you try to pursue a solution and that you realize that it won't lead to a full solution, so you backtrack and then try another possibility, because there are lots of possible solutions, lots of possible expansions or extensions. Choice matters. Okay,